Today we're going to do limiting reactant and percent yield. And you should have an introduction to limiting reactant already from the s'mores activity we did in class. And percent yield is fairly simple. It's just a percentage. So we're going to talk about that and do a few examples. All right, so back to our cheese sandwiches. If you're making a cheese sandwich and you have 10 slices of bread and 3 slices of cheese, how many sandwiches can you make? And I think we all can do this one in our head because it's such a familiar example. So 10 slices of bread can make us a total of 5 sandwiches, right? Because we know we need 2 slices of bread for each sandwich. 3 slices of cheese can only make us 3 sandwiches. So in this case, we're going to run out of cheese before we use up all our bread. So our cheese is our limiting reactant. And we're basically going to go through the same steps we did in the previous problems, but this time we have to do it twice, once for each of the different reactants that we're given. And then we choose the one that's going to give us the smallest amount of product because we'll run out of that one before we can make more. And that will be our limiting reactant. Okay, so if we take an actual chemical example, if we have carbon monoxide plus H2 gas gives CH3OH, then if we have 3 moles of carbon monoxide and 5 moles of H2, how many moles of methanol can be produced? The first thing we need to do is make sure that our equation is balanced. So we have 1 carbon on each side, we have 1 oxygen on each side, and we have 4 hydrogens in our product and only 2 in our reactants. So that means we're going to have to add a 2 here before our H2. All right, and that's important to make sure your equation is balanced before you begin your problem. All right, so if we have 3 moles of CO, and we know for every 1 mole of CO, we can make 1 mole of methanol, then we know we're going to make 3 moles of methanol. All right, we have 5 moles of H2, and we know that we need 2 moles of H2 to make 1 mole of methanol. Okay, so in order to do that, we need to divide, and then that will give us 2.5 moles of methanol as a product there. So even though we're starting with more moles of H2, that is still our limiting reactant because we need more of that to make our product. All right, so the answer is we can make 2.5 moles of methanol, and our limiting reactant is H2. Now, if we're given grams and we want to find grams of our product, we're going to go through the same gram-to-gram conversion that we did in the last lesson, and the same process we just did on the previous slide. We'll do it both for CO and for H2 and see which one gives us less, and that will be how much we can make, and it'll also be help us determine our limiting reactant. So first we're going to set up our plan. So we're going to go from grams of the reactant that we're given to moles using the molecular weight, and then we'll get to moles of methanol using our balanced equation and the mole-mole ratio, and then we can get to grams of methanol using the molecular weight of that. Okay, so first we need the molar mass of carbon monoxide, which is 28.01 grams, and the molar mass of H2, which is 2.016 grams per mole, and then the mass of methanol, which is 32.04 grams per mole. All right, and then we're going to set up both of the problems. We're going to do 5 grams of CO, because that's what we're given, times 1 mole of CO is 28.01 grams, times 1 mole of methanol uses up 1 mole of CO, and then times 32.04 grams of methanol in 1 mole. And that will give us 5.72 grams of methanol if we use up all of our carbon monoxide. All right, for the hydrogen, we have 5.00 grams of H2 times 1 mole of H2 is 2.016 grams times 1 mole of methanol requires 2 moles of H2 times 32.04 grams of methanol in 1 mole. All right, and when we multiply all of those numbers out, we get 39.7 grams of methanol in this case. So we clearly have a lot more hydrogen here than we have carbon monoxide, and so carbon monoxide is our limiting reactant, and if we use all of it up, we will get 5.72 grams of methanol. Right now on to percent yield. So percent yield is a fairly simple concept. It just tells you how much you got compared to how much you should have gotten if everything went perfectly. So an example, that's sort of a real world example, if you're making s'mores and you have enough supplies to make 50 s'mores, but you have so many to make that you load up your stick with 5 marshmallows to save you time, and while you're roasting, you get distracted talking to a friend, and they get so melty that they slide off the stick and into the fire. So now you have 45 marshmallows instead of 50 because you lost 5 of them. But you're much more careful roasting the remaining 45 marshmallows, and they all turn out perfectly and make delicious s'mores. So your theoretical yield would have been 50. So you had enough supplies to make 50 s'mores, and that's what should have happened. But actually, things happen in life, and you don't always get all that you should. You ended up with 45. So one thing to note is that your actual yield should never be bigger than your theoretical yield. You can't make something if you don't have enough supplies to make it. All right, and so then your percent yield is going to be what you actually got divided by what you should have gotten times 100. Okay, so this is not much different than calculating your grade on a test, right? You take the points you actually earned divided by the points you theoretically could have earned and multiply by 100. So in this case, we're going to do 45 divided by 50 times 100, and that gives us a 90% yield. All right, now let's take this one step further and do percent yield for an actual chemical reaction. So here we have lithium hydroxide plus carbon dioxide yields a lithium bicarbonate. And the question is, what is the percent yield of lithium bicarbonate for the reaction if 50 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? Okay, so first we need to figure out what our theoretical yield is. So it tells us in the problem what our actual yield was, that's 72.8 grams. What we need to figure out is how much we should have made. And all we know is that we started with 50 grams of lithium hydroxide. So let's figure out how to get from grams of lithium hydroxide to grams of lithium bicarbonate. And so we're going to do the same process we've been doing, going from grams to grams. So first we need the molecular mass of lithium hydroxide, which is 23.95 grams per mole. And then we're going to need the molar mass of lithium bicarbonate, which is 67.96 grams per mole. Okay, and then we can set up our calculation. So we have 50 grams of lithium hydroxide times 1 mole of lithium hydroxide is 23.95 grams. And then we're going to multiply that times our mole-mole ratio. And we didn't double check, but this is a balanced equation, so our mole-mole ratio is 1 to 1. And then the last thing we're going to do is go from moles of lithium bicarbonate to grams using the molar mass. So there's 67.96 grams in 1 mole of lithium bicarbonate. All right, when we multiply all that out, we get 141.9 grams of lithium bicarbonate. Okay, so we know from our equation that I gave you for percent yield that we want to take the actual yield, which is 72.8 grams, divided by our theoretical yield, which is 141.9 grams, and multiply that by 100 to get the percentage. And when we multiply all that out, we get 51.3%. So we only got about half of the product out of this reaction that we thought we should. Okay, so this wraps up our discussion of limiting reactant and percent yield. We're going to do some more practice with these in class and do a little bit of hands-on experience in the lab.